Hey folks, today we're taking a look at this. This is a high vacuum chamber that I've been slowly assembling over the last couple weeks, and honestly I've been accumulating parts for at least a couple years now. I've got a few different projects planned for this chamber, and rather than explaining how the high vac works in all the different project videos, I thought I'd just do a single video kind of describing the chamber and all the different components so people can get an idea of how it works in a dedicated video. And then the project videos can just be about the projects, and I can refer people back to this one if they have questions about how high vacuum works. So at its heart, this is basically just a big box that doesn't have any air inside of it. The difference between this and like a resin degassing chamber is that it's designed to get to a much lower pressure. So it has much better vacuum than you would get kind of just off a simple vacuum pump. It accomplishes that with two different pumps, a roughing pump down here and a turbomolecular pump at the top. And then everything else is basically just accessories to make that system work. So I'll bring you in closer and we'll look at all the different components, and I'll show you the procedure for pumping it down to its ultimate pressure. We'll start down here on the floor. The most important part of the system really is this unit here. This is a rotary vacuum pump, and it provides the rough vacuum for the whole system. So this can drop the vacuum pressure down to about 1 millibar or so. It's spec'd for better than that, but once you get to around 1 to 10 millibars, the turbomolecular pump on top of the chamber can take over. So the point of this is really just to extract the majority of the gas in the system to start. It does that by rotating a vane inside a chamber full of oil and mechanically displaces the gas and sucks it out of the chamber. So these things are super robust, they can get pretty good pressure, and they're not expensive to find on eBay because they're basically everywhere. My unit has a couple interesting or important features. Over here is an oil mist eliminator. These things kind of spew an oil mist out of the exhaust, and if you don't have some type of filter on it, you'll very quickly have oil mist all over your shop. So these are pretty important, or you just pipe it outside. On this side, this is the inlet, so this is where we're pulling the gas out of the chamber. You can see there's a canister down here at the bottom. This is full of a copper mesh, and the point of this is to help eliminate what's called backstreaming. So even though this is the inlet where the gas is going this way, some amount of oil vapor will come back up and work its way into the chamber. And you don't want that because that oil vapor will contaminate whatever you're doing. So this canister basically just has copper mesh to help condense and drip the oil vapor back out. More sophisticated systems will have like liquid nitrogen traps to condense all the oil vapor, but I don't need anything that fancy for my system. Above that we have a T here that contains an air valve. This lets me open the bottom section of pump to atmosphere, and a ball valve which disconnects it from the rest of the system. This is useful if we want to keep vacuum in the chamber but turn off the pump. We can close off the ball valve and then open up the pump itself to vacuum. And that's important because if you leave this under vacuum without the pump running, it will slowly suck oil up into the system and you'll kind of foul everything up. So it helps to relieve pressure when you can. Over here we have the various electronics that control the system. This is the turbomolecular pump controller. We'll see more about that in a minute. It's on top. This is my vacuum gauge, which can read pressures from atmosphere all the way down to ultra high vacuum levels. And then below it, this is a mass flow controller for devices like this, which allow you to very precisely add gas into a chamber. And so this is the controller for it, although it's not currently hooked up and doing anything. So on the top here, we can see where most of the business is happening. Got a bunch of flanges that have a variety of different things attached to it. In the back left here is a vacuum gauge. So this is what's connected to the controller down below, and this provides the current reading of vacuum pressure inside the chamber. Union here that has two different attachments. On the top is another air valve, so this allows us to admit air into the chamber. When we're done with whatever we're doing, we can open this up to quickly vent it. And then over here is a T that comes to a gas union. And this allows us to open this needle valve and admit some type of processed gas into the chamber, whether it's like an inert gas, argon or nitrogen, or something like oxygen or hydrogen. Whatever you want, you can put through a valve like this. And then ideally, this would be connected down to the mass flow controller so that we can very precisely control the amount of gas coming in, because a needle valve like this isn't very precise. This hose right here comes from the roughing pump, so all of the rough vacuum is coming out of this hose down to the pump. That brings us over to this section where we have these two devices. These are both manual valves, so we can open and close these to change how the gas moves through the system. If we open this valve, it allows gas to pass through this union down into the chamber. So this is basically the kind of roughing valve. We'll open this up at the beginning to allow most of the air to pass out of the chamber through this T here. And then this valve goes to the turbomolecular pump, which is this big unit back here. So the turbo is what lets us get down to high vacuum levels. As I mentioned before, the roughing pump will get us down to, say, 1 to 10 millibars, lower if you give it time. The turbo is what gets us to high or maybe even ultra high vacuum levels. It's too complicated to really go over in this video, but a turbo works by spinning a set of rotors inside of this cylinder against a set of static stators, and that action of like rotating vanes slowly compresses the gas up through the turbo and out the exhaust hose. The rotors spin at about 50,000 RPM on this unit. Some are faster, some are lower, just depending on kind of the geometry of your particular turbo. The trick with turbos though is that they only work once you get to a minimum pressure. So if you were to run this at atmosphere, it'll spin really fast, but it doesn't actually compress any gas, so you won't get any vacuum. So you have to have a roughing pump running in the background to first evacuate the chamber to rough vacuum levels before the turbo can even do anything. My particular turbo, as you can see, is mounted upside down. Not all turbos can do this, so make sure you check the specs before you mount it like this. Some of them have oil-filled bearings or other arrangements that can't work upside down or at an angle. Mine works in any orientation, and this particular flange is the best option on my chamber for mounting, which is why it's here. As you can see, there's this conical reducer here. So my turbo has what's called an ISO 100 flange. That's kind of this section here. And the flange that it's attaching to is a KF50. So they're not the same, and you need an adapter to connect the two together. This isn't ideal having an adapter like this because the reduced kind of volume inside of the adapter slows down how quickly it can pump. So ideally this would be mounted to a similar size flange to get maximum pumping speed. Below that you can see a little valve here. This is a butterfly valve that allows me to close off the turbo from the chamber. And this combined with this valve over here means we can isolate the turbo from everything else. This is convenient if we want to vent the chamber and then get it back to vacuum relatively quickly. We can close off the turbo here and here, isolating it to its own little environment, vent the whole system, bring the system back down to rough vacuum, and then reopen these valves to let the turbo continue working. And this is helpful because turbos take a really long time to spin up and slow down. I think mine takes 10 or 15 minutes to get up to speed, and it can take up to an hour to slow down if you don't admit any gas into the chamber. So having a shutoff valve like this and keeping it running is just a good time saver when you're wanting to open and close the chamber a couple different times. Looking at the chamber itself, it's currently under vacuum, so I can't actually open it, but the front side here is the door. So this is how you get into the chamber to do whatever you're doing inside of it. And you can see here there is a port that has some glass on it so you can look to see what's going on or shoot lasers or do whatever through this port. Ironically, this port is an ISO 100, and so that would match perfectly with my turbo. And when I was testing the system, I had it mounted here and it pumps down great. The problem is that it's on a swinging door, and so you can't really have everything rigidly connected to this port because the turbo has to be disconnected every time you open and close the door. So I'm not really sure why the chamber was designed this way. I got this used on eBay, came from somebody's lab, and they had a reason for this, but typically you find a big port like this on the top or the bottom for something like a turbo rather than on a door, and this is kind of odd. On the two sides are these giant windows, and honestly this is what kind of caught my eye about the chamber to begin with, and the reason I got it was these giant windows. This is very uncommon for most chambers. Typically they'll be made out of stainless steel in like cylinder shapes or spheres, but it's just a lot of metal and you only have little ports to look through. So this is pretty unusual, having not one big window, but actually two on two different sides. And so this made sense for me because I want to film stuff in here for the channel, and having two big windows will make my life just a lot easier for filming. It'll also be helpful for high speed capture because I can shoot a high intensity light through one side, station the camera in front of it to collect all that light, and then look at some type of process happening in the chamber under high speed. So I think this will be really helpful for filming, and it's just really cool to have this much like visibility into a chamber. I'm curious what the prior owners use this for. I've really not seen a chamber like this before, and it's really something special. On the side opposite the door, you can see we just have these 6 flanges. These are all KF40, I believe, quick change flanges. Don't have any use for them at the moment, but this will be great if I want to put electrical feed-throughs or gas feed-throughs or some type of, manipulators. All these extra ports, it's always handy to have them. You want more ports than not. Oh yeah, I should mention there is one little flange on the bottom. It's just a little KF16 flange, so it's real small. I don't know what it's doing down there, but that's technically an option if I ever need it. So my system uses exclusively a type of flange known as KF flanges, or also sometimes known as NW. This is a common type of flange that you'll find on lots of kind of mid to high vacuum gear. Once you get into ultra high vacuum, you tend to see more CF or Conflat flanges. I'll show that to you in a second. But mine exclusively uses this KF quick change system. The way it works is that there is a flat face on one side and a tapered edge on the other side, which accepts a centering ring, which is basically just a ring that has an O-ring or gasket material. It sits in the middle of the flange face, and then you take your other side and that sits like so, and the centering ring keeps everything, well, centered. And the two tapered edges then engage with a locking clamp, which holds it together. And then you give it a bit of a squeeze and engage the screw. And as you tighten this down, it pulls these two sides together, which because of the tapered edges on the KF will cinch the two together and tightens the O-ring. So you just give it a couple of twists, and now that is locked and vacuum tight. This works with hard fittings like these or hoses like this. These are stainless steel hoses to give you a little bit of flexibility in your arrangement. It attaches different types of barb fittings, or like we saw on the machine, things like valves or anything else you'd want to connect to the system. There are different types of centering rings that you can get. So you can see this one is black. There's also brown, and I have some green ones. And they're not just colored, these are actually different material. Green is typically Viton, which has better outgassing and vacuum performance, but it's more expensive. I forget which is which. One of these is nitrile, and one of these is, I don't know, something else, probably like polyurethane. So there's different types of centering rings you can get for different applications. And of course, there's also different flange sizes. So these are KF16, which is the smallest size. You can also get KF25, which are a little bit larger. And then this one is a KF40, larger still. And I think they go up to KF50 or so. And after that, you switch to a different system called ISO. Now the KF system is really handy because you can basically Lego your way to a system really quickly, because everything quickly comes on and off using these centering rings, and it's very easy and simple. The downside to it is that you're using polymer to lock in the vacuum, and polymer can do a good job. Like Viton is pretty good at holding vacuum, but it outgasses a little bit, and it's not a perfect seal. And more importantly, it has a temperature limit. So you can't heat these polymer gasket seals too hot or else they'll start to melt. And this is problematic for ultra high vacuum systems because you have to bake those systems at high temperature to drive all the water moisture off the walls of the stainless steel chamber. And so for those systems, you tend to use what are known as conflats. This one is wrapped in foil to protect it, let's peel it open. Conflat, or CF, is a system that uses a metal gasket inside rather than a polymer gasket. I mean, you can use polymer gaskets, and that's a common way to do it, but they don't provide as good of a seal as something like this. So this is a piece of soft copper. This one's been used, and so I'd have to throw it away now. And the idea is that the CF flange, don't know if you can really see that on video, but there's a sharp knife edge inside of this flange. And so when you mate two pieces together, the soft copper actually digs into the stainless steel flange and creates a metal on metal seal. And this gives you really good vacuum sealing capabilities and is what lets you get down to ultra high vacuum levels. So CF is better for high vacuum. The downside is that this copper is a one and done. After you use it and take it apart, you have to throw it away. So it's better for systems that don't need changing often. And it also has multiple bolts that you have to torque down as opposed to just a quick change. So each has their place. Mine system just doesn't come with any of these, so I don't really have to worry about it for now. Ultimately, that means the vacuum level of my chamber will be limited because these O-rings will always be the limiting factor, but that's fine for the stuff I want to do.
Okay, let's take a look at the sequence of events to get this chamber pumped down to its ultimate pressure. First, we go through and close all the valves that open to ambient atmosphere and open up the valves between the roughing pump and the chamber. Then we turn on all the electronics and the roughing pump and let it pump down to about 100 millibar. During this first part of the pump down, we have the gas ballast open on the roughing pump. This helps the pump evacuate air that has a lot of water vapor in it, just, humidity, and keeps it from contaminating the oil quite as much. Once we get down to about 100 millibar, I like to close the gas ballast. The gas ballast is helpful, but it reduces the final pressure. We open the valve on the turbo pump so that it can start pulling more air through the turbo itself. We don't do this to start because we don't want dust and particles to get sucked through the turbo, but at this point there's so little air in the chamber that it's okay to open it up, and this will evacuate it quicker. Now we can turn the turbo on and let it start to pump down. For my unit, you just short 2 pins on the controller and it'll start to spin up. We close the valve between the roughing pump and the chamber, so now that all the gas is being evacuated through the turbo and out the turbo's exhaust. If we didn't do this, then some of the gas that's compressed out the turbo will just escape back into the chamber through that roughing line, so we want to make sure we close it off to get the best pressure possible. And then we just let this pump down. We can get down to kind of low 10 to the minus 6 millibar. This is kind of a mid to high vacuum range, and to be honest, I'm pretty happy with it. For context, the generally accepted edge of space is the Kármán line, which is 100 kilometers above the surface of the Earth. And that's at about a 10 to the minus 3 millibar. By the time you get up to the International Space Station, you're at about 10 to the minus 7 millibar. So we're somewhere between the edge of space and the ISS.
Cool. Well, I hope you found that interesting. Like I said, I've got a lot of stuff planned for it, but I want to just give an overview of how this whole system works before we dive into the actual projects using the chamber. If you enjoyed today's video and are looking forward to more high vacuum experiments in the future with this chamber, make sure you're subscribed so you don't miss anything coming up. Big thanks to all the people that support me on Patreon. I really appreciate it. And I think that's all I got for you. Thanks for watching. I'll see you next time.